Hello there, and welcome to this video on Parallax. Let's try a simple experiment right now. There is a red circle on the screen. Hold your thumb out in front of you, but keep your eyes on the red circle. Cover or close one eye. Now open that eye and cover or close the other eye. Do you notice how your thumb moves with respect to the red circle? Now move your thumb closer to you and repeat. Close one eye. Now open and close the other eye. What do you notice about how far your thumb moves this time? Well, it should move a bigger distance. This apparent movement of your thumb with respect to the fixed circle is known as parallax, and it's due to the different positions of your eyes when you are looking at your thumb with respect to the red circle. To have a closer look at this experiment, we can draw it out and we can use trig. Here is a schematic of the experiment. The two blue circles on the left-hand side of the screen represent our eyes. The green circle is where our thumb was, and the red circle represents the red circle that was on our screens. If we could measure the apparent angle of displacement of our thumb during the experiment, then we can use this to calculate the distance between our thumb and our eyes. This angle here, this would be the full displacement of our thumb. However, we only need half of this angle in order to do this calculation. To find the distance between our eyes and our thumb, we can use trig. Here I'm going to use tan of the angle equals opposite, which is half the baseline, over adjacent, which is the distance between our eyes and our thumb. We can rearrange this to make lowercase d the subject. Therefore, we have an expression for the distance between our eyes and our thumb. Since the angle of displacement, or the apparent thumb movement, gets smaller the further away our thumb is from our eyes, there will come a point where we won't be able to see the apparent displacement, so this experiment does have its limitations. So parallax so far seems pretty cool, but you might be wondering, well, why am I doing a video on it? Well, parallax is one of the methods that astronomers use to calculate the distance to nearby stars. Now, I've emphasized nearby because, like I said before, if an object is too far away, then this method is no longer feasible. So there is a limit to how far an astronomer can use this method. So how do astronomers use parallax? Well, we basically have this experiment on a larger scale. However, for astronomers, the eyes would be the Earth. So one eye would be the Earth in orbit in January. The second eye would again still be the Earth. However, it would be the Earth as it's travelled around its orbit of the Sun 6 months later. So it would be the Earth in July. The thumb, or the green circle, would be the nearby star with which we want to measure the distance to. And the red circle would be background stars that are so far away that they don't appear to move at all, so they appear fixed. By viewing and photographing our target star, first in January, and then waiting 6 months, and then in July, again viewing and photographing the star, we can measure the star's angular displacement relative to the fixed background stars, and using what we just derived from trig, we can calculate a rough estimate of the distance to the nearby star or our target star. This angle here is known as the parallax angle, as this is the angle that we use to figure out the distance. Remember, the parallax angle is half of the full displacement. I do have a little side note though regarding parallax angle and astronomy. Normally in maths we use angles in radians. However, in astronomy we don't measure the displacement angle of a star or anything in the sky in radians because radians would be too big and we'd end up with 0 point something something something. So instead of measuring the displacement using radians, astronomers use something called Arcminutes and Arcseconds, which I'm going to explain right now. In astronomy, we measure the angular displacement using Arcminutes, or more likely, Arcseconds. Here is a circle. Imagine this is the equator of the Earth. When we're looking up at the sky, we can split the field of view up into degrees. In 1 degree out of the whole sky, it's still a big field of view, so astronomers came up with the idea of then further splitting this 1 degree into 60 different segments. These are called arcminutes and are denoted with a little dash. 1 arcminute is still a relatively big field of view when we compare the actual displacement of a star from parallax. Therefore, each arcminute can be further split up into 60 sections called arcseconds, and arcseconds are denoted by double dash. This means that for every 1 degree field of view of the sky, we have 60 arcminutes, or 3,600 arcseconds. Since we measure the star's displacement using arcseconds, it would be helpful if we could find a relation between arcseconds and radians, which is what we would normally use. Just before I do find a relation between radians and arcseconds, I want to go back to this image. I've also included the equation that we derived before using trig. If you notice, the distance between the Sun and the Earth is denoted by a capital D. However, in astronomy, the average distance between the Sun and the Earth is known as an astronomical unit. So in this equation, I'm going to sub capital D and put in 1 AU instead. The parallax angle is most likely going to be very, very, very small. So using the small angle approximation, tan of an angle will just tend to the angle's value. Therefore, I can change the bottom of the expression, get rid of the tan, and just leave it as the angle. We already know that this angle is in radians, however, it's measured in arcseconds, so we do need to find a relationship between radians and arcseconds. A circle has 360 degrees, or in radians, 2 pi radians. Since we already know a relationship between arcseconds and degrees, if we can express radians in terms of degrees, we can times it by 3,600 arcseconds, and then we'll have an expression relating radians and arcseconds. So if 2 pi radians are 360 degrees, then 1 radian is equal to 360 degrees divided by 2 pi. To get radians in terms of arcseconds, we must times it by how many arcseconds there are in 1 degree. And when we put all of this into the calculator, we get a value so there are approximately 2.06 times 10 to the 5 arcseconds per radian. Now that we know this, we can use this to our advantage when it comes to the angle in radians. Going back to our expression, since we are measuring this angle in arcseconds, we need to find an expression for the angle in arcseconds. Well, all we need to know is how many arcseconds per radian. All we need to do is take our angle in radians and divide it by how many arcseconds there are in 1 radian. I'm going to sub in the value for 1 AU in terms of kilometers. We can simplify this further. .086 times 10 to the 13 kilometers is known as 1 parsec. A parsec is defined as the distance to an object or a source if the parallax angle is 1 arcsecond. The distance, in parsecs, is 1 over the parallax angle as long as the parallax angle is in arcseconds. This is the expression that you've most likely seen, and this is what astronomers use to measure the distance to stars. Like I mentioned earlier, eventually there will come a point where a star is just too far away to measure any parallax angle to a degree of accuracy, or sometimes any parallax angle at all. So this method does have a distance limit. Well, that's it for the video. If you found it helpful, please like and subscribe and hit the bell so you can stay up to date with my videos. If you would like to request a topic for a video, do write it in the comment section below and I'll do my best. But thank you for watching and have a good day.